Alright, so we're working through some exercises in the SVD, so this is page 53 in that exercise section. And let's take a look at a couple more. How about we'll take a look at number 5 and 6. Number 5 says that if the vector x is a linear combination of v1 through vn, then the magnitude of ax squared will be alpha 1 squared lambda 1 plus alpha n squared lambda n. And so of course the v's are coming from the evex, or they're from the SVD, or you could think of them as being the evex of A transpose A, right? Good. So let's see how this is going to work. Um, let's see, the magnitude of ax squared is ax transpose ax, right? And so that's going to be x transpose A times x. Of course, you might see what's coming now. That's x transpose, and then A transpose A. Let's take the SVD. That's going to be, oh, wait a sec. One point here. I guess I could just maybe let's pause here for a second. Okay, I just wanted to construct. I was just about ready to write A transpose A times x, right? And this stuff right here, I want to reconstruct and using the eigenvectors. Okay, so I'm going to go ahead and erase that. And let's go ahead and compute this then, because this is easy. Remember now, the v's are the eigenvectors of A transpose A, and so I can rewrite this expression as alpha 1 times lambda 1 times v1 plus alpha n lambda n times vn. Right, so then I'm going to take x transpose and multiply that times this. So let me rewrite that. Let me go ahead and just bring that down. Maybe I should have worked this out in advance so it'd be a little cleaner. So that's going to be x transpose times this thing, which is alpha 1 lambda 1 v1 plus alpha n lambda n vn. And of course, what's x transpose? That's alpha 1 v1 plus, let me just go ahead and bring in the transpose while I'm at it. And then I'll go ahead and I'll have this one. Now this is a lot of stuff to keep track of, but it's not too bad because the v's are orthogonal to each other, right? So let's see, when I multiply this times this, I'm going to get alpha 1 times alpha 1 squared times lambda 1, but then v transpose times v is equal to 1, plus, and then if I multiply through by the rest, right, by orthogonality, that's just going to be a bunch of zeros until I get to the next one, right, which would be alpha 2 squared times lambda 2 plus a bunch of zeros. And then I continue that until I get to the last one. And so that's going to be similar, alpha n squared lambda n times 1, vn transpose times vn. Good, plus a bunch of zeros. Good. And so, yeah, this then is true by orthogonality. Good. If you don't believe that, you could just try a couple, maybe two vectors instead of n, and then you could multiply it all the way out. Yeah, you can take a look at that if you like. Number 6. By the way, we're going to use this property later on. This is a really important property that we're going to use. So let W be the span of those eigenvectors, but now we're going to run from k plus 1 up to Vn, right, where the rank of A is k, and the V's are the singular vectors, the right singular vectors, are the evex of A transpose A. Okay. What we want to show is that W is actually equal to the null space of A. Okay, and so let's see if we can show it both ways. So I'm going to start by finding or taking something in W and then showing that it must be in the null space. Similarly, then we'll take something in the null space and show that it must be in W. Okay, so let X be in W. Then I'm going to show, instead of showing directly that it's in the null space, I'm going to show that the magnitude of A times X must be equal to 0. In fact, I'll just go ahead and square that. And because if you have a vector, let's say U is equal to, oh, not U, I'm using U for something else. What's a good, yeah, if you have the magnitude of something equal to 0, S, then S must be 0, right? Okay. That's by property of the norm, right? The only thing that has norm 0 is the 0 vector. Okay. Gosh, I'm running short of time. Let's see, AX squared. I think you've seen this trick now. X transpose A transpose times AX, right? That's X transpose A times X. And now, if X is in W, right, then X is in the span of these. And so what can we say about that? Oop. That's equal to, oh, didn't we already show that? Yes, we did. What is lambda k through k n plus 1? So this is going to be alpha 1 times lambda k plus 1. Let's go ahead and say k plus 1 squared plus alpha n lambda n. But the lambda i's are all 0, right? And so this is equal to 0. And so therefore A times X is equal to 0. Good. And so therefore X is in the null space of A. Very good. Similarly, let's see if I can move this thing around. For some reason it's not doing what I want. Let X be in W. Show that X must be in the null space of A. Oops, that's what I just showed. I want to start with X in the null space. Show that it must be in W. Well, let's think about what we're doing here. X is in the null space, therefore A times X is equal to 0. In order to show that X is in the W, that means that it's in the span of the 0 eigenspace, right? And so what happens if I take A transpose times A times X? Do I get lambda times X? Yes, right? Because A times X is equal to 0. A transpose times 0 is 0. That's equal to 0 times X. Good. Therefore, this vector X is in the span of the 0 eigenspace. Good. All right. So those were just a couple of exercises. We went through them pretty fast, so you might take a look at them again if you like. We might take a look at one more video real quick, just to take a look at the 4 fundamental subspaces and the SVD. I don't want to get too long-winded about the SVD, but it's just so darn important. Okay, I'll see you in the next video.